make it more generic. Because what could be better than taking numbers out and sticking just letters in? I think everybody enjoys alphabet soup. Any questions before we generalize it even more? Just so you know, I haven't done this part before, so we're just going to jump into it and see what happens. And as with any of the impromptu, hey, let's just see what happens kind of things, at some point I might go, wait a second, something's wrong. And hopefully we didn't make the mistake the first time, but we should end up with the exact same answer if we make it slightly more general. I know that we'll call this theta 1, and this is theta 2. This angle down here should be what originally called theta 3 is the same as theta 1. So this angle up here, this 30 degrees, this is theta 1. So this just becomes tangent of theta 1. Our 19.2, that's coming from Snell's law, because we had N1 sine of theta 1 equals N2 sine of theta 2. So I know sine of theta 2 is equal to N1 over N2 times sine of theta 1. Oh, this is going to get ugly fast. I'm now having second thoughts about doing it more generic.
Yeah, I'm already lost. Yeah, me too.
Yeah, I probably should crank through it myself on my own first before I subject you to it. All right. Sorry to do a little tease there, make you think, oh, all right, we're about to do a lot of, alphabet soup on the board, and
Something to look forward to.
yeah. Now, do recognize that one of the things that we have here is I had light coming in through air, hitting glass, and going through it. I think most of you at some point have experienced the fact that light doesn't always just hit the glass and be done with it. Most of you have seen reflections off of glass plates. So there is some light that is bouncing off and some that is not. So as light comes in, you're going to have a certain part that gets reflected and a certain part that's going to go through. This angle here would be the same as the angle of incidence. This is just angle of reflection. This is the same as the angle of incidence. When light gets down to here, again, we're changing medium, and it's possible that some of it's going to bounce off also. So as light hits here, it's going to have some reflection, and then it's going to shoot off at what would be a 30-degree angle here when it comes out. So if you are here, that's your eye. This light is going to hit your eye, which means there's a possibility that if the thickness is just right, you're going to get interference patterns. We'll hold off on the interference. Is that this chapter or the next one? Yeah, that's coming up later. So I guess that's just a tease for the moment. All right, so let's take this other scenario where I've got air here. I have glass, is it crown or flint? Which one was this?
I think it was crown.
Crown? All right. Crown glass here. What you missed is that I opted not to do the more generic one. I was going to go through it first because it was going to get ugly fast, and so. All right. So if light's coming in this way, let's make this 30 degrees. I know it's going to bend farther away. What is that angle? And again, my index of refraction here is 1.52. My index of refraction here is roughly 1. what is this angle here? How would you find it? We can do it individually. I was thinking somebody would just chime out of how you would actually go about solving it, but you know, either way.
Do it the opposite way we solved the last one, right?
Yeah, it depends on what you mean by opposite,
I
but
mean, for the first part, instead of the inverse sine of 0.5 over 1.52, it'd be inverse sine of 1.52 over 0.5.
no.
We would set n1 sine theta 1 to equal n2 sine theta 2.
All right, so there's our first start. So n1 sine theta 1 equals n2 sine theta 2. All right, what's n1?
1.
What's theta 1?
We don't know.
Okay, so I have 1 times sine theta 1 equals
1.52 sine 30 degrees.
okay. So sine theta 1 is equal to 0.76. So theta 1 is the arc sine of 0.76.
.46 degrees.
That seems reasonable. The note I have here is I was using the other glass when I did it before and came out with a almost a 55-degree angle. So index of fraction's not as great, so the angle's not as great. So that seems reasonable. Suppose instead of questions up here before I change it. Suppose instead of 30 degrees, we made this 40 degrees. What's theta 1 now? So 77.69, I think I heard.
Well, the 9 is rounded, so it's 0.7.
All right, suppose we make theta 50 degrees. And by the way, William, traditionally, if you're doing 1 and 2, 1 is where the light starts and 2 is where it ends up. There's absolutely nothing wrong with what you did by setting theta 1, n1 equal to 1. Traditionally, it would have been set to equal to 1.52. The only difference, the equations would have been flopped. So it would have been 1.52 times sine of 30 degrees equals 1 times sine of theta 2. It's a notational thing, but just in case you're looking in a book, you might go, wait a second, why is that one theta 1 or that one theta 2? Lisa, did you get an answer?
It says I get domain error.
Domain error.
That's what I'm getting to, so I'm gonna get.
Well, let's take a look at that. So, I have sine of theta 1 is equal to 1.52 times the sine of 50 degrees. What is the sine of 50 degrees?
.766.
And if I multiply those together, what do I get? Why is it? We've got several people with this with the same domain error or ease or whatever your calculator flashes up error. Why? How could you have known that you would have gotten an error before you actually did the arc sine?
Because it's bigger than 1.
Yeah, it can't be bigger than 1. So what is that limit? What is that angle that we would get there? In other words, I want sine of theta 1 to be equal to 1. Well, given our index refraction here is 1, this is 1 times 1 equals 1.52 times the sine of theta 2. I'm trying to figure out what angle am I going to hit, do I first hit that error? So sine of theta 2 would be 1 over 1.52.
degrees.
41 degrees.
41.14.
So assuming that that's exact, at 41.1 degrees, that's the point in which it doesn't actually leave the surface. It doesn't. That's the point at which the angle, well, actually, at what angle is the sine equal to 1? Degrees. So at 41.1 degrees, so that's 41.1 degrees, the reflection is 90 degrees. This is, in the textbook, they call this the critical angle. This is the point when you have total internal reflection. And so we can summarize that more generally. Nothing as complicated as what I was about to do earlier. We have N1 sine theta 1 equals N2 sine theta 2. Given our notation before, so theta 1 is 90 degrees. This is that point, that reflection there. So I have N1 times 1 equals N2 times sine of this critical angle. And so sine of the critical angle is equal to N1 over N2. This builds in the assumption that we have theta 1 is equal to 90 degrees, that the reflection angle, it hits the surface and then basically shoots along the surface itself. So this assumes that N1 is less than N2. If it's the other way, if it's going to, using better language, this would be angle of incidence, and this is the angle of refraction. So it assumes that the angle of incidence is greater than the angle of refraction. Wow, that is, I should not be using that notation there. It is just a wonderful day. Angle of incidence, angle of well, it's not angle, that's wrong. It's the index of refraction of the incident of the initial material. I'll just put F for final. If it's going the other way, if it's going to something with a greater, if it goes to a greater index of refraction, it's going to refract. There is no critical angle. It's only when you go from a higher index of refraction to a lower index of refraction do you possibly get this. And this is the essence of fiber optics. Because you have some piece of glass or whatever, fiberglass, whatever, you have some sort of material there with a higher index of refraction than the air surrounding it. And so you shoot it at an angle so that the beam doesn't, you don't lose it by its going outside the beam. It will hit the edge, and then it will basically shoot along the side of it.
So it's
Or-
just bouncing around.
Yeah, it won't leave. Assuming, of course, that you don't have a sharp bend in it. Questions to hear? There's one other way that you can see this refraction happening. Actually, there's several ways of getting the refraction to happen. Refraction is also specific to the frequency or wavelength. So index of refraction is it's a function of the material itself, so we'll write it that way, it's a function of the material and the wavelength of light. So as light hits a material, it's not necessarily going to bend the same way depending upon what the frequency of light is. So what is one place where you see this index of refraction varying because of the wavelength of light?
Say that again.
What is a place in real life that you see this index of refraction being different depending upon the wavelength of light? Where light bends differently depending upon the wavelength. Perhaps a more fundamental question is, how can you differentiate the wavelength of light?
Color.
Yeah. So where do you see color?
Rainbows.
Gavin, you had that?
I was thinking it the entire time, but I didn't think it was right.
Believe in yourself. Have faith.
Rainbows.
Rainbows, yeah. Because rainbow happens when the light is going from air into a water droplet. And so light comes in, it is going to bend differently depending upon the light, which will then come back out. And so it starts to split it. Now it's not going to split it much with just a single drop, but if you have enough drops, then it slowly over time will start to differentiate and you start to see the colors. Also classic prism. I guess the cover of Pink Floyd's Dark Side of the Moon. I think you've got the prism there also. And
So how does that work with colors we can't see?
with colors you can't see,
Yeah.
it still works that way. I assume you mean not colors you can't see, but light that you can't see
Yeah.
outside the visible spectrum. Let's make sure I get this the right way. So the higher the frequency, the higher the energy. The higher the energy, the less it deviates. And so the lower energy light will bend more. So another place you see it, sunset. So Earth, you are here. You are huge. So when the sun is here, relative to us, the light's coming in. What's going to bend the most are the red lights, which have the lowest energy. And so the red light's going to hit. Yeah. So energy of light's dependent on the frequency. So as the frequency goes down, it bends more. Light bends more. Frequency going down means the wavelength is going up. All right, so microwaves will bend far more than ultraviolet. What that allows is, because radio communications tend to be radio communications tend to be a lower energy than visible light. So what this allows is for easier spying on other countries. Because as the radio waves are sent out at a lower energy, they are more apt to be bending through the atmosphere. So you don't actually have to be visible there to see them. You just need to be there so that when the light comes around and when the electromagnetic radiation comes around, you can get it. So it still works for that too.
So is radiation kind of like light? They're at a really high frequency?
Okay, so I was using radiation and light almost interchangeably. Electromagnetic radiation is light. Generally, when people say light in everyday life, they mean visible light, but in physics, light's a much broader category, whether you can see it or not. Radiation itself, there's three major types of radiation in terms of, things that can cause cancer.
I just think like X-rays.
Yeah, the X-rays would be considered light from a physics point of view. But the three major types of radiation that you see are called alpha, beta, and gamma radiation. Gamma radiation is just basically light. Alpha radiation is a positively charged ion, is basically a helium nucleus. And beta radiation is the electrons. So
Okay, so there's actual particles moving in the other one.
alpha and beta are actual particles moving. Gamma radiation is, I hesitate to say they're not particles because we'll eventually get to the point where we really start talking about the particle wave duality of everything. But from a classical physics point of view, it would be waves.
What's the most dangerous?
High energy, I would say high energy electromagnetic radiation.
Is that like what happened in Chernobyl?
Alpha or gamma?
Which one would that be?
Be like gamma.
Did you watch Chernobyl?
I did. I'm trying to remember that. It seems like that was given off everything. Because the dangerous part is you've got the DNA helixes inside your cells, and all you need is something is to basically change it, to knock an atom out of place, to lose an electron, and so forth. So the dangerous stuff is what's called the ionizing radiation. It's the radiation that can cause a molecule in your body to lose or gain an electron, and therefore once it does that, it is now going to be attracted to something else, and so another molecule will attach itself to it, which potentially causes a cell to multiply out of with fewer checks to it.
Is that kind of like cancer?
That is cancer.
Okay.
I think the underlying thing, if I understood my mom correctly, the thing that makes all cancers cancer is the unchecked growth of the cell. So that's why if you're doing chemo, it basically kills all the fast-growing cells, which is why the esophagus and the stomach gets so eaten up, because that's where we have our fastest-growing cells. That's my understanding. Again, last time I took biology was 1979.
Is that hair too? Like, is hair fast growing? Is that why people lose
Yeah, I guess,
hair?
yeah, that too. But that adds to the stomach sickness aspects of chemo. Just in my limited understanding of it. Mom would start talking this stuff, and then pretty quickly she'd get in the language I don't understand.
Is your mom a doctor too?
She was in medical school, but ultimately she dropped out to get married. She said, I don't regret it, it's just what she did at the time. It was 1960. She ended up being an oncology nurse in the end. So, Mom was not the most upbeat person, but then she goes into oncology and, you know, my favorite patient died today.
My sister's a rad tech, so it's
Oh.
kind of similar. Patients dying on her and stuff. Like, how do you do that?
I have no idea. Then I thought, well, go to something nice like pediatric, but then I'm thinking, all you need is one kid to die, and then suddenly that would wreck you even more.
Piggy poison, I guess.
Or stay away from medicine altogether and just be the patient.
Yeah. Deal with electronics.
Nice thing about physics is, a human body is just another object. All right, any other questions at the moment?
Is that like the northern lights? Like aurora borealis, how like that light reflects?
That is, you have radiation coming from the sun, and as the radiation comes in, it excites. Suddenly. This interaction of the radiation from the sun with our atmosphere. Since we have atoms in the atmosphere, I'm suddenly thinking of two possible explanations. So here's my possible explanation number one. The radiation comes in, it will hit an electron in an atom, which will then move to a higher orbital. Because you have the atom here and electrons traveling around in some orbital right here. You get temporarily, the electron will move to a higher level, stay still within the atom, move to a higher level, but it's not stable like that, so it'll collapse. When it collapses back down, it loses radiation, and that radiation happens to be the visible spectrum. The other possible explanation is that you get the electrons are now have enough energy to leave the atom. And so now you have a charged particle traveling, and charged particles traveling create magnetic fields, and with the right, I guess if they hit just right, then it creates electromagnetic radiation. Basically, a moving charge creates a magnetic field, so potentially you could have electromagnetic radiation being created, which is also light. I'm not quite sure which one it is at the moment, because that is just the way my mind's working today. Other questions at the moment? Especially now that Curtis is out, we can ask important questions.
Why is he in this class?
God only knows. Oh, by the way, by the end, I'm going to head back to tests. Just so you know.
Thank God.
Oh, no.
Are they worse than usual?
No, I wouldn't say worse than usual. No one failed. That makes you feel any better.
Oh, okay. Makes me feel a lot better.
Everybody demonstrated that he or she knew something.
Wow, it's like the participation award in a sentence.
There are enough tests where I'm going, this person has learned absolutely nothing. So, that I cannot always make that statement truthfully.
It's worse.
The other place that you would also see that light bends in the atmosphere is mirages also. So because light travels differently, so why this sky is blue, because when the sun is here overhead of us, you have light bouncing going off in all directions. Red light is gonna bend more, and so the red light basically bends away from us, or my drawing is horrible, but the spirit of it is bright. And so what we basically are hit with is the blue. This makes it look like the sun should look blue, and that's not the intent there, but the sky looks blue because that light is not refracted the most. But at sunset, sunrise, it is refracted the most. The blue light's gonna be going more directly. The red light gets bent, and we see the red sunrise or red sunset. And so mirage is also, so temperature plays a factor in the index in terms of it affects the material. And so if you're in a very hot area here, light is coming down, and yeah, you're basically seeing the sky. That's the mirage. So it looks like a blue pool of water in the distance is actually just the refraction of the sky coming at you.
Is that kind of the same thing, like on the road, when you're looking ahead, you can kind of see it kind of looks reflective a little bit, way off in the distance?
Yeah, I would say that probably is the same thing on a hot day. You can see that something is happening, because on a hot day you can see sort of that wavy line in front of the really hot road.
Yeah.
Yeah, the advantage of teaching this in the South is I'm sure everyone's experienced this part. And so, yeah, that's index of refraction messing with the light.
I always wondered about that. That's basically a mirage.
Yeah, I think
Like
officially,
a baby mirage.
was
That's
that?
like a baby mirage. Like a little
I think you can safely say that, yeah.
Okay.
I generally don't see blue in the distance, I just,
Yeah, it's just like mirror. It kind of looks like a mirror, or like.
yeah, I'm trying to think of, it would have to be hot and on a really long straight road, I would think,
Yeah.
which pretty much eliminates most of the roads in the South. I guess I-40 might have some stretches that really,
I've seen it going towards the beach.
okay.
There's some pretty straight ones there.
And presumably out west, where I swear if you had good alignment, you just put a car in cruise control and fall asleep, and the thing would just stay on the road. I have not tried it. Please don't try that.
I think you could.
I've never had a car with good enough alignment, so.
The new cars do that now.
The
They
self-driving?
have Automatic, well, they don't self-drive, but they have automatic steering where they stay within the lines.